How are you, ladies and gentlemen? Today I want to discuss about strengths of materials. This knowledge is derived from the book Fundamentals of Engineering Science by G.R. Titcomb, but I've tried to find some further information for you to be able to understand the importance of strengths of materials. Many engineering components are subject to different types of forces. These components include electric lines, machines, and different structures. Some of the structures, to mention a few, include buildings, bridges, towers, tanks, etc. Furthermore, there are different types of machines carrying different types of forces. These include towers, conveyor belts, vehicles, cranes, and aeroplanes. It is therefore important for an engineer to understand basic strengths of materials to enable design of the components. It is important for the engineer to be able to select the types, shapes, and sizes of materials required to resist the forces. Of course, these I'm teaching you as basic if you are aspiring to study engineering. Forces. Newton's laws of motion states that to every action there is an equal and opposite reaction. Therefore, when a force acts on a body, the body will provide reaction force to resist the applied external force. There are different types of forces which act on solids, some of which are compressive forces. These are perpendicular to a surface and have a direction towards the objects. Compressive forces tend to push the areas when they act. Then we have got tensile forces. These act perpendicular to the members and have direction away from the members. These tend to pull the surfaces of the objects. Shear forces. These are parallel to the surfaces and have a tendency to cause the surface to slide against each other or to tear apart the surfaces of the objects. So you should know the difference between the tensile, compressive, and shear forces. This is a figure. Figure 1 illustrates the compression forces. You can see the forces acting towards the object. So it causes compression. It is pushing the surfaces of the object. Then figure 2, you've got tensile forces tending to pull the object. They are moving away from the object. Then you have got figure 3, which indicates the shear force. The shear forces, they are acting parallel to the surface. For example, they can cause shear forces on the two objects and cause them to slide against one another. And you can see that the two forces, the two members are connected by a rivet, so they tend to tear apart the rivet, as you can see. So this is an example of a shearer. This is called a shearer because it tends to shear apart. If you want to for example, to tear apart maybe the feathers of a sheep, or you want to tear apart something else. So you have this is called shearer. So this should enable to understand what is shear force. Shearing, shear force. Introduction to stresses. When a force acts on a body, it causes stresses. The body will develop reaction towards the force until the body can resist no more, and therefore it fails. The ability of the body to resist the forces depends on the type of materials. The force acting on a body per unit area is defined as stress, and the unit of stress is Newton per millimeters squared. Introduction to stresses. When a force acts over a given area, it causes stresses. You can see here sigma, which is the stress, is equal to force over area, where F is force, A is area, sigma is stress. There are different types of stresses which act on solids. The most common of them are tensile stresses. These act perpendicular to the surface and has a tendency to pull the members. Compressive force stresses. These act perpendicular to the surfaces and have a tendency to push the members. And then you with shear forces. These act parallel to the surfaces and has a tendency to cause the forces to slide, to cause the surface to slide against each other. And the result of the shear stresses on a body are tearing apart. So you can see a diagram, figure 5 indicates compressive forces which are acting towards the surface. You've got tensile force stresses which are acting apart from the which are acting away from the member, and then you've got shear forces. You can see shear stresses. You can see that there are shear stresses on the plates which are connecting, on the rivets which are connecting the plates. Can you see the rivet now? The rivet is tending to be torn apart. You can see the one applied force is pulling one part of the stress, or one part of the rivet to go on the left side and the other on the right side. So this is tearing apart. Mind you, shear and tearing. Examples, I have some examples. For example, a wire, a 2.5 millimeters in diameter, is subject to a tensile force of 500 Newton. Compute the tensile stress in the wire. The cross-section area of the wire, A, is equal to pi d squared over 4. You have that area, 4.91 millimeters squared. And then we've got stress is equal to force over area is equal to 500 Newton over 4.91 millimeters squared. So you get 101 Newton, 0.8 Newton per millimeter squared. Another example is the compressive force. You can see the compressive force acting on a column. A force is acting on a hollow column, having an external dimension 400 millimeters by 400 millimeters, and internal dimensions 200 millimeters and 200 millimeters. Compute the stresses on the column. Figure 9 indicates the compressive forces. So the force is acting towards the column and it is causing stresses. So as we said, stress is equal to force over area. Area is equal to 400 times 400 outside south dimensions minus 200 times 200 inside dimensions. So you've got this area of 120,000 millimeters squared. So you've got sigma, or stress, is equal to force over area is equal to 2,000 times 10 power 3 Newton over 120,000 millimeters squared. We've got 16.7 Newton per meter squared. That is the stress, compressive stress acting on the column. Here is another example of tensile stresses. A piece of timber, 50 millimeters by 50 millimeters, is the capacity of carrying tensile stress of 5 Newton per meter squared. Calculate the force which can be carried safely by the timber. Figure 10 indicates the table. Gives an example of tensile forces on a piece of timber, which is 100 by 50 millimeters. So we have got stress is equal to force over area. Force is equal to stress times area. So you've got a stress of 5 Newton per meter squared times area, which is 50 millimeters by 100 millimeters. And you've got a force of 25 Newton, which is 25 kilonewton. Example, shear stresses. For example, you have 150 Newton per millimeter squared of shear stresses acting on 6 bolts, each having a diameter of 50 millimeters. Compute the total shear force acting on the 6 bolts. Solution: force is equal to stress times area. Stress is equal to, this is stress is 150 Newton per millimeter squared. Area is equal to 6 bolts times pi times 50 millimeters diameter over 4 is equal to 11,775 millimeters squared. So force is equal to stress in Newton per meter squared times area. Therefore, we got a force of 1,765,250 Newton, which is about 1,766.25 kilonewtons. Another example of shear stresses, you can see here you have got a beam which is glued to a column, and there is a vertical force acting on the beam. A force of 200 kilonewton is acting on top of a beam. The beam is held on a vertical column using glue. Calculate the shear stresses on the glue joint. Solution: the glue joint between the beam and the column has got dimension 200 millimeters by 200 millimeters and is causing a reaction force acting parallel to the force of 200 kilonewton. Shear stress is equal to F over A is equal to 200 times 10 power 3 Newton divided by 200 millimeters by 200 millimeters. Therefore, you got a shear stress of 5 Newton per meter squared. Note the shear stress is parallel to the glued surface between the beam and the column, and is trying to cause failure by causing sliding between the two surfaces. And ascending strain. When a force acts on a member, it causes changes in dimension of the member. This change can be elongation in terms of tension, shortening in terms of compression, or twisting in terms of shearing. Strain is the ratio between the change in dimension and the original dimension of the members. So there is delta S change in length over original length in terms of tension and compression. So the strain is the ratio between the change in dimension and the original dimension, where L is the original length, delta L is the change in length. Please note that for tensile forces, the members will increase in length, while for compressive forces, the members will decrease in length. For shear forces, it will be twisted. This is the typical load extension diagram for tension in ductile materials. Typical diagrams for ductile materials. You can see there is load, a graph between load and extension. Normally, the load will be increasing up to elastic limit, where the member, the length of the member can return to its original dimension, and normally it is proportional. The load divided by extension, the load is proportional to the extension. But when it reaches elastic limit, the extension starts to increase more than the increase in the load until it reaches a yield point. At lead point here, you will find that the material now will start increasing in length. It will start to extend without any further application of the load. And after time, it reaches the maximum load that the structure can carry, and it reaches fracture at the end of the day, where the member have failed. So it reaches fracture. So strain, you can see figure 13. It indicates a horizontal force acting on some spring leaves, which are tied by a certain, say, bolt or rod, and normally it starts to move horizontally, as you can see. So you can find that X will increase in this direction, and the original length is L. So X over L is equal to shear strain. So shear strain is defined differently from tension and compression. Description of behavior of tensile materials. When forces are applied on materials, the member is stretched with the force. When force is released from the member may return to its original length if it is within elastic limit. Materials are said to be elastic if the material can return to its original size after removal of the applied force. According to the Hooke's law, the stresses applied to a member are proportional to the strains in the member within the elastic limit. As you can see the diagrams again, this is the elastic limit from 0 up to here, where the load and the extension are proportional. So we say they are within the elastic limit. So within the elastic limit, the stress and the strain are proportional. But after that, then they don't obey by what we call Hooke's law. Hooke's law. When a material is in elastic stage, the stress is proportional to the strain, and it obeys the formula E is equal to sigma over eta, where eta is strain, sigma is stress, E is the modulus of elasticity. So this is constant when it is in elastic stage, and this is called Hooke's law. Description of behavior of tensile material. Mathematically, we have this formula, as I said, And E is called the Young's modulus of elasticity. Beyond the elastic limit, they don't obey the rule. For shear stresses, this constant is called modulus of rigidity. So this is called modulus of elasticity in terms of tensile and compressive strength, but in terms of shear forces, this is called modulus of rigidity. Load extension diagram for brittle material. For brittle material, like a cast iron, you don't have the what we call the elastic stage. This is characterized by sudden failure under tension, such as cast iron and concrete. Figure 16 indicates stress and strain diagram for brittle materials. Shear strain. So this is shear strain, as I have said that, as I have shown that if you have got a number of strings connected by a rod and you move them horizontally, then they'll go to through a distance x and divided by the distance L, you have got the shear strain. Strength of material. In engineering, strength of material is the capacity of the material to resist stresses without failing. Normally, in design, the engineers ensure the materials are made to carry stresses below what they can actually carry before failing. The ratio between the maximum stresses which the material can carry before failure and what it is allowed to carry in practice is called factor of safety. Factor of safety is ultimate strength over the working strength, or what we allow the materials to work under. So you allow them to work under lower amount of load. So F is the safety factor that you don't allow your material to be loaded up to the ultimate strength.